Any questions before we start? Let me remind you all. The last math club of the semester will be on Friday. It's going to be on math modeling. It looks like it's going to be kind of a fun talk. Don't forget the math in Saturday from 10 to 5. And also, obviously, we don't have a final in this class, but we will get together during finals time to, I don't know, I'm not going to take the full final period on that, especially since it's my youngest birthday and I've got to go take care of that. But we will get together on that day and have a kind of a final, kind of wrap it up lecture. Okay. So I wanted to pick up where I left off last time. Did everybody kind of get that last example? We did an evaluation domain. It wasn't a theory, and so last time. So we started off with this kind of generalization of polynomials where I'm going to have my coefficients out of the field of 2 elements out of Z2, but it doesn't have to be that. It can be, I can work this for any fields. And we let M be the maximal ideal. Let's say epsilon I, x alpha I, where so basically we look at this maximal ideal consisting of all polynomials, and I use that loosely, that have a 0 for a constant term. Right? This is a maximal ideal. It's fairly easy to see because if you look at this ring here, we call this R. Because you're letting all powers vector to 0, so to speak. So this is maximal ideal. The quotient is isomorphic to Z2 or F2, using that interchangeably here. And so if you look, this localization is valuation domain. And my argument was this. B in a localization, a typical non-zero element of B looks like a fraction here, where the numerator is a non-zero. That's why I mean, not 0. The numerator is a non-zero element of B, and S is an element that is not in the maximal ideal. So basically, S is like one of these generalized polynomials that has constant term 1, right? So V is associated, a non-zero, right? Because SV is equal to R, but S is of course a unit in the localization, and that means that I might as well, if I want to, I'm going to try to show this is valuation domain by showing the two non-zero elements, one of them divides the other. Instead of looking at B, which complicates my life, I might as well just look at R, right? Because it varies by a unit. And so notice that R is equal to, well, it's equal to epsilon 0 plus epsilon 1 x alpha 1, epsilon 2 x alpha 2, epsilon n x alpha n, or here we'll assume alpha 1, alpha 2, alpha n, and because I can certainly arrange it that way. And so notice that if epsilon 0 is 0, then R is equal to x to alpha 1, epsilon 1 plus epsilon 2, x to the alpha 2 minus alpha 1. And notice that this is a unit. We can assume without loss of generality that epsilon 1 is not 0, because if it was, I would just move this other up to epsilon 1, and they can't all be 0 because then I've got 0, and I said this wasn't 0. So notice that this is associated with x to the alpha 1, because this thing right here is a unit, right? Because this is not 0. And so given any two non-zero elements, are non-zero, then E1 is unit 1 x to the alpha 1, and E2 is unit 2 x to the alpha 2, where UI, where units would be, and alpha 1, alpha 2 are in 2 plus units. And of course, whichever one has the smallest alpha divides the other. So this is evaluation. Here's what this valuation domain looks like. Anyway. So, like any good local ring, what happens? Well, this is actually a quasi-local ring. Outside the maximum ideal, you have units. Right? When you have only one maximum ideal, everything outside of it has to be a unit, as opposed to Z. If you take something out of the ideal generated by 2, like 7, it's not necessarily a unit. When you've only got one maximum ideal, you got that going for you. And this maximum ideal basically consists of everything that looks like this for alpha greater than 0. Right? Notice that is not generated. Here's my proof of this. Suppose if not, M is generated by x to the alpha 1, x to the alpha 2, x to the alpha n, alpha 1 plus alpha 2, alpha n greater than 0. you can show this because any generator that you pick is one of these things up to a unit, right? But note, X, the alpha 1 over 2 is not in M. And in fact, what do you know about any finitely generated ideal in the valuation domain? Its principal. So in fact, this ideal would be generated by the smallest, x to the smallest power. And that makes it even clearer, right? Because there's no power, or there's nothing you can multiply x to the alpha 1 by and get x to the alpha 1 over 2. It's too small. So this can't possibly be finitely generated. However, the maximal ideal is the radical of the principal ideal. In fact, take any element of M other than 0, anything in M other than 0, and the radical of that would be this maximal ideal. Because here's what the prime ideals look like this: 0 and M, and that's it. So if you take any x to the alpha, then the radical of this ideal, or the radical of x to the alpha, is all of M. Because notice that radical of, let me make that clear. The ideal generated by x to the alpha is M, where alpha is anything bigger than 0, because I'm being a little sloppy because I'm only writing exponents here, but again, up to units, that's all I need. Notice that first note, alpha is A over B, where A and B are in the integers, and B is not 0. Well, actually, yeah. Actually, A and B are in the natural numbers. That's a little bit better. Right. Beta is x over y, with x and y in the natural numbers as well. Notice that x to the beta, the y, let's see, I need to find the beta. Yeah. Notice that this large power of x to the beta, right? I want to claim that that's in the ideal term by x to the alpha. This is, actually, I might need a bigger power here. Beta y is x, this is x a. I guess I want it to be. There we go. Bigger power. This is x. Oh, do I really have to call this x? Oh, my bad. I'm doing calculus. Let's call this z. This is x to the z, AB. Which is let me see, I'm screwing up this thing here. So notice x to the alpha equals x to the A over B, so x to the alpha B is x to the A. Okay. So notice this is x to the A is EB, because I didn't need so many powers after all, which is in the ideal generated by x to the alpha. Because x to the A is in the ideal generated by alpha, so certainly this large power is. So here's what we've done so far as far as building examples. I think I may have used this word in 8510, the spectrum of an ideal is this collection of prime ideals. So one, the valuation domain has only the prime ideal 0 as a field. This is actually true. You don't even have to use valuation domain. Integral domain that zeros its only proper idea or only prime ideal as a field. Yeah, integral domain. If it's dimension 1, this bifurcates. If M is finitely generated, then M is principal. And B is a local PID. This is called the Noetherian valuation domain. Some people use the terminology discrete valuation domain. I do not like that terminology because it's misleading. Commutative algebraists, actually, commutative algebraists are provided as well for discrete valuation domains. Some people think it means Noetherian valuation domains, and some people think it means something else. If you see the word discrete valuation domain in a number theory class, then what they're probably going to mean is the Noetherian valuation domain. However, when I use the word Noetherian valuation domain, there's no confusion. And I'll show you that there are discrete valuation domains by definition that are bigger, that are not Noetherian. We've got value group, composite C. I'll do an example of that. If M is not then B is one-dimensional, non-material. But we've seen ideals that come up like this. I gave you an example from number theory, where you took the ring of all algebraic integers and you localized a maximal ideal that contains 2. They're infinitely many to pick from. Or this sort of polynomial-esque example that we have. Anybody figure out how to build a bigger one? One of my favorite examples. And you can generalize this, and you can also mix and match with the idea. 4. I'm going to build valuation domains like this. Zero will be a prime ideal, of course. and it'll have an intermediate prime ideal P. It'll have a maximal ideal, By the way, do y'all remember a theorem that I gave you in like 8510? I think we had it back then, but well, I don't know if I told you this or not, but a ring R is Noetherian. What is it? Does anybody remember what it means for a ring to be Noetherian? Or the equivalent definition?
Something about those chains are stabilizing.
That's right. It satisfies the increasing chain condition on ideals. Another way to, I like this, it's fine, it's kind of simple-minded, is that all ideals are finite generated. Right? That's what it means to be Noetherian. All ideals. Y'all remember this theorem that, so what it means to be Noetherian is it means that every ideal is finitely generated. So in particular, every prime ideal is finitely generated, right? And the converse is true. So here's what I mean. A ring is Noetherian if and only if the prime ideals are finitely generated. Do y'all remember me talking about that last time? So if you believe that theorem, and here's a nice application of this. When I build this valuation domain, it's got three ideals that are prime. That's it. The maximal, 0, and this intermediate one. And I'm pretty sure that one's finitely generated, right? Now, if it's not Noetherian, one of those other two has to not be finitely generated. Let's take a vote, shall we? Which one, or both? So what are my outcomes? I know at least one of them's got to be finitely generated. So it's either P is not finitely generated, M is not finitely generated, or both M and P are not finitely generated. And actually, I can build it multiple ways here. Okay. Anybody want to guess which one has to be not finitely generated? Why do you think P?
Just a guess.
It's a good one.
From messing around with 2G on the present homework. I'm thinking about this kind of stuff.
Very good. Yeah, so here's the deal, right? I mean, generally speaking, I mean, if you look at, this is what I find kind of weird about this. This is one thing that's kind of different. Like a lot of commutative algebra is focused in doing things in the theory, right? And if you want to go look at that, go take a look at Carrie. Carrie does a lot of things where her rings are Noetherian, and she looks at things, you can attach sort of geometric things to it. And there's finiteness conditions in the theory. They're restricted, right? And so that they can make theorems work and so forth. Here's a couple of things that I find surprising, right? If you look, so let me give you a nice Noetherian here. As the prime ideals get bigger in the stack, you expect them to have more generators, don't you? Right? So, for example, like that. But actually, I'm going to build one where this ideal is not finitely generated, and this one is principal, which is kind of strange. Right? There's also an interesting theorem. If you have a Noetherian, given the Noetherian domain, and you have two prime ideals, like these two, if you can find a prime ideal in between them, like this one, they're infinite. This is only true in general for Noetherian, right? Which is kind of weird, right? Because Noetherian, you've got the finiteness condition, but Noetherianness actually forces the existence of that P in a Noetherian ring would necessitate the existence of infinitely many prime ideals between. And you can kind of test this out, right? Because here's a good example right here. There are infinitely many there's infinitely many prime ideals between this one and this one, because you can start going crazy. You can go, right, and you can start doing stuff like this, x plus 1, comma y, x plus 2, comma y, et cetera, et cetera. Can't do that. This is valuation domain, and the primes are linearly ordered, right? So there's no way that you can have multiple in between there because they have to be linearly ordered. That's a couple of kind of surprising things where here the not finitely generated makes the prime ideals behave in a more orderly fashion, if you will. So let's build one of this type. Two elements here. Right, so let's do this.
Just to say, it's always kind of interesting that, like, if this were a field, obviously 0 would be the only one, but if it were a field, then the multiplicative part of the ring would be an abelian group, which would also imply that if P was finitely generated, then M would have to be finitely generated because of abelian. But because we don't have
Right.
then that makes this condition. But it's kind of silly with rings.
Right, because I mean, if you have a field, 0 is the maximal ideal in the first place, right? So I'm going to look at the following collection of rational functions. So take the field and take two polynomial determinants, x and y, right? But I'm going to add some more stuff to this. And I never stop. So this is the smallest ring that contains x and y. So it's got all rational functions. Or I'm sorry, not rational functions. It's got all polynomials in x and y. But it's also got these extra rational functions. Notice that it doesn't have 1 over x. But notice that the way I've set this up, every power of x divides y. I'm sort of setting up here for valuation domain, right? Because as it stands right here, this is not a valuation domain. Why not? Because look at x plus 1 and y. Y certainly doesn't divide x plus 1, and x plus 1 doesn't divide y. Right? What an annoyance that is. So here's what I'm going to do to make this valuation domain. Let M be the maximal ideal generated by all these rational functions, x, y, y over x squared, and so on. Notice that R mod M, if I call this R, is a field. And so therefore, this is maximal ideal. But B R localized to M. This is valuation. Let me kind of go through some of the details here. Again, every element of V is associated to an element of R. So I'm going to kind of, so instead of worrying about fractions, I'm just going to worry about elements of R, pull out units and so forth. I claim, given any pair of elements, either one of them divides the other one. Notice that given this pair of elements, x and y, x divides y, because you've got that thing. Right? Notice given this pair of elements, x divides y over x. In fact, x divides y an arbitrarily large number of times. Everybody okay with that? Of course, here's the problem. Things get a little bit more complicated when we start doing things. So how can we write element R? Let's write it as a x plus b y plus c1 y over x plus c2 y over x squared. Oops. Well, this isn't a typical element bar because of course you've got products in there too, right? You have things in there like x, y, and you have y squared over x to the fourth and y squared over x cubed and so on, right? But let's just look at this. Notice that x, if a is not 0, then you can pull an x out of this, right? Everybody agree? Then we can pull an x out of this. Notice this is a unit. In fact, let me make a further judgment. If you have anything, any sort of polynomial that you can make out of these rational functions, then if there is an x term, you can pull that out of everything. Everybody agree with that? Because x divides anything with a y in it. And x is the lowest power of x that you can have. Yes.
By saying if a is not equal to 0, then we can pull this like that. Do you mean then this would be a unit? Because can we pull this out? Can we? I mean, if a is 0, can we still pull an x out? But are you saying because a is
Yes,
0?
yes.
Then
What
this is a
I want to
unit?
do is claim that this element is x times a unit. Right. I could certainly pull an x out of that, but it didn't do me any good, right? If a is 0, and I'm gonna bring this all together. If a equals 0 and Cn not 0. Notice that I can pull the y over x in out of this. Right. What's it now?
Do you want a equal to 0 or not?
I want a equal to 0. Thank you. And in fact, let me point out that the following can be shown. Any element of these is a form is 0. A power of x times a unit. I can sort of collapse these. I'm kind of spreading this out. Or it's the form where k is greater than or equal to 1 and n is an integer. And U is a unit. Similar to this example here, right? Notice what's different here. Let me make it clear. You know, it's an actual number or 0. So if n is 0, then this is a unit. If n is greater than or equal to 1, then this is a non-unit and it's just power of x. And if your power of y is at least 1, now you've got complete freedom with your x's. You can go negative if you like, positive or negative. So in other words, any two elements of this is essentially one of these types of monomials. Notice that, you know, a couple of observations. If you have x to the n u1, x n1 u1, and x into u2, one divides the other. Depending on whichever one has the smaller exponent. Right? So if I compare two elements that look like this, one of them divides the other. 2, x to the n u always divides an element of the form y to the k x to the m u prime. Or k is greater than or equal to 1. Because you can always jerk out as many x's as you want out of that. And finally, this is the hard one. What if you have y k1 u m1 x m1 and what if you have that where here k1 and k2 are greater than or equal to 1? Well, and in fact, let me say this. We'll say K2 is smaller. Which one divides the other? Yeah, it depends, right? So notice that YK2 M2 X M2 divides YK1 X M1 if K1 is strictly bigger than K2. Right? That is to say, if when you do the division, there's a little bit of, if there's a little bit of Y left over, then it doesn't matter what the power of X is, and this one divides it. The big question is what happens if they're equal? What happens in the tie? What happens at the last time? Then you go to the X. This is a less graph order. If you have a tie and the exponent on the Y's, look at the exponent on the X's, whichever one's smaller. Everybody okay? So it turns out, you know, I was kind of fast and loose with this, but it turns out that any element of this valuation domain is a monomial of one of these two forms, right? Non-negative powers of x or positive power of y in any power that you like. Right? In this valuation domain, you have the zero ideal, and then you have the maximum ideal, which is generated by x. Notice if you go back here, notice that it makes sense that the maximum ideal is generated by X, because actually X divides every single one of these generators, right? Just by the way I constructed it. Right? By the way, I gave you an example at the beginning, and I said this isn't a valuation domain because of, if you look at y and x plus 1, neither one of them divides the other. What happens now in the localization? Which one divides? Which one divides? Which one? In the original ring, neither one of them divided each other, but after I passed the localization, one of them's got divided. Otherwise, my whole example, I've wasted everybody's time. It's all, whole example's wrong. If you can't think of it yourself, put your heads together and think it's a unit. Correct. X plus 1 in the localization is a unit, right? Because X is in the maximal ideal. So X plus 1 is actually not in the maximal ideal. It turns into a unit. So in a silly way, it divides by. Because in the valuation domain V, I'm allowing 1 over X plus 1, right? So that's what happens here. Now, at the zero ideal, at the maximal ideal is generated by X, it divides everything in sight. It's not a unit. And then you've got this weirdo middle ideal. And it's not generated. You always need more generators. So here's this prime in the middle. Notice that if you look at the group of divisibility, do you remember one of the things that we used to define the valuation domain is I said, okay, we start with a field and there is a function from the field into a totally ordered abelian group, yada, yada. Yeah, anybody know what the totally ordered abelian group here is? 2 copies of C, ordered lexicographically. Right. So have y'all ever seen the library order where you do a value group? Is and I always get the order of this wrong, so bear with me. Where the ordered pair, well, let's go A, B is less than or equal to M, if and only if A is less than or A equals M is less than. Everybody, okay? How many of you have seen this before? She worked in the library. That's right. If you've ever looked up somebody's number in a phone book, of course, you guys probably don't even know what a phone book is. But if you've looked up somebody's name in a phone book or tried to find a book in the library, what do? Oh, I want to find, My Life by Polly Shore. Well, what I do is I start with the M's, and okay, so I get to the M, but oh no, it's MA, right? And so I go MB, that's a strange book, and I have to go until I get to my MYs, right? And that's exactly what you're doing here. It's the library order, the lexicographic order. If A is less than M, then yes, this was actually in the L's, not the M's, right? If you've got a tie, you look to the second letter to break your tie. And that's exactly what we did with these exponents, right? You can think of the A and the M as exponents of Y, and the next one is the exponents of X. And what do? We compare the exponents of Y, and if they're the same, even if they're 0, then we had to move on and look at the powers of X to break the tie, right? This is the value group here. What are the positive elements of this? 0, 0. So this is, remember, our valuation domain, right? I mean, this value group is basically the quotient field. The valuation domain was all the stuff that was positive, right? So the valuation domain was, remember that it's the set of everything that have value greater than or equal to 0. Okay, for this, what are the values that are greater than 0? Well, let's see. Well, let's see, if A is greater than or equal to 1, or A equals 0 and B is greater than or equal to 0. So translation, what elements do we find in the valuation domain? Anything that looks like this. One and in anything. Or x to the n in greater than or equal to 0. By the way, if you can do the library order on any number of copies of Z, can't you? Right? You can have 3 copies or 4 copies or however many you want. You can use that totally ordered group to build a valuation domain that's bigger than this one. Right? If you have 3 copies, it'll be of dimension 3. So you'll stack your primes 0 and then 3 non-trivial ones. You can build bigger and bigger and bigger with that. If your value group is some finite number of copies of Z, say n copies of Z, with lexicographic order, this is what many community algebras call a discrete valuation domain, because it's lexicographically a finite number of copies of Z. Okay, any questions on that? You can do this with infinitely many copies. You can also lexicographically order Z in real numbers. You can go just bananas with this stuff, right? And you can build all kinds of crazy, crazy valuation domains. You can build them so big that they don't have a minimum non-zero prime ideal. There's a lot of crazy stuff going on with those. Okay, any questions on that? Okay. I think actually, I'm gonna finally prove that theorem that I swore to you I was going to. We have, I guess, 2 more lectures, and so I want to talk a little bit about Dedekind domains and whatnot, prove some stuff about finitely generated, and we'll probably finish some of this on exam week, I would guess. But next time, what I'm going to do is I will prove for you what I promised about the value of the integral closure being the intersection of valuation over rings, and then we'll start talking about Dedekind domains. Any questions? How about out there? Any questions out there? Okay. All right. Well, y'all have a good one, and we will see you on Friday.